Hi everyone. So last video I finished up with the definition of mass. I told you that mass is the stuff that any object is made out of. There is one definition that's fairly close to mass, but I would really like all of you to, make this clear for yourself that these are not exactly the same. And that definition is weight. Weight of any object is the force of the planet that object is basically on towards that object. So we live on Earth, okay? Because of Earth, we know that acceleration due to Earth is 10 meters per second squared, okay? Now, because of this acceleration, I told you, whenever there is acceleration, there is a force of m times that acceleration. Now, force that is directly related to the acceleration due to Earth is called weight. It's that simple, right? So let's say I have a block of gold, let's say 2 kilograms of gold. Now, the weight of this gold on Earth is 2 times 10. This is the weight of the gold, 20 newtons. What we mean by weight is this much force is exerted on the block of gold by Earth. Earth pulls this block of gold by 20 newtons towards its center. Okay? Now, what if I bring the gold, exact same block of gold, to the moon? Here is the moon. If I bring the 2 kilogram gold to the moon, acceleration of the moon, let's call it G prime, I think it's 6.5 meters per second squared, somewhere around that. So weight of this gold on the moon is now 2 times this acceleration. And it's about like 13 newtons rather than 20, right? So please make sure that you understand what is the difference between weight of something and the mass of something. Weight is some sort of a force. Mass is something that depends on the nature of the object. Okay? Mass never changes. The 2 blocks of gold that's on Earth, if I bring exact same amount on the moon, that block, the stuff that's inside it, never changes. Therefore, mass never changes, as long as it's the same thing. However, weight depends on where the object is. Weight is essentially the force of gravity of any planet on the object. Is that clear? So let's say Jupiter. Jupiter is way, 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 way bigger than any planet you can think of. This is Jupiter. Now, if I bring the exact same 2 kilogram of the block of gold on Jupiter, then the weight of gold of this block on Jupiter is 2 times gravity of Jupiter. I don't know, 25 meters per second squared maybe. That gives you 50 newtons already. So depending on which planet you live on, and this block is situated, depending on where this block is, then that planet will give you will exert some force on this block, and that force is called weight. So it is related to mass, but it is not exactly mass. Weight changes depending on the G that relates to the planet we live on. Different G's are having different G's give rise to different weights, right? Weight is force, mass is something that's due to the nature of the object. Okay? So that's one thing I really want everyone to notice, and that's very important. The other thing is, let's just elaborate more on the Newton's second law, which is F net equals m times a. So I said F net equals mass times acceleration. So whenever an object with mass m accelerates with an acceleration of a meters per second squared, there has to be some net force acting on it. What do I mean by net force? Net force means summary of all the forces, resultant of all the forces, adding and subtracting all the forces and the last number you end up with. This is what I mean by net. Okay. For example, if I have a block of mass, let's say I have a block of mass of 20 kilograms. So that's pretty big. If I have a block of mass 20 kilograms, and then I push by 10 newtons this way, my little sister comes and she pushes it by 5 newtons. Then there is this naughty boy that wants to, resist against our pushing force. He pushes it by 2 newtons. Net force becomes 10 plus 5 minus 2, right? So that gives you already 13 newtons. So net force means adding all the forces that are in the same direction and subtracting whatever forces in the opposite direction. Okay? That gives you the net force. So that's pretty much what I wanted to stress about for Newton's second law. Now let's go to the third Newton's third law, and let's finish all the laws of Newton. Then in the next videos, I elaborate a lot more on Newton's second law, and then we do free body diagrams and all that sort of stuff. So stay tuned for the next videos. But let's wrap up because I finished the first law and second law by now. There is one law that I have to cover, and then after which we basically move on with the rest of the material. So Newton's third law is law of action and reaction. Basically, what he says is, imagine there is this cannon, and the cannon shoots a ball. Okay, you always please go and go check it out and search it on YouTube. You see all these recoils from cannonballs or any gun or something. So this recoil is due to the Newton's third law, which means that if the cannon pushes the ball with this force of F, the ball pushes the cannon in the opposite direction, but exact same amount. Because the forces are exactly the same amount, and because force is m times a, because both forces are exact same amount, and the cannon itself is so much bigger than the ball, so this is way bigger. That's why its acceleration is way smaller, just because the forces are the same. So say you have two forces of mass of the ball and mass of the cannon, right? So if these are the same and the magnitude of them is the same, whichever is lighter, here the ball, gets more acceleration. Because, the mass here is way lighter, Hence, the acceleration gets bigger. Here, the mass for the cannon is way bigger, the acceleration is smaller. That's why the recoil is way smaller compared to this, you know, to the ball where it actually lands way, way further away, right? So that's the reason. And this is basically Newton's third law of action and reaction. If A exerts force on B, B exerts exact same amount of force on A in the opposite direction. I'll explain more about Newton's third law in the next video because this is getting a little bit long. Bye now.